second speaker of the day is Sami Halaseh, and talks about moment as hierarchy on the product of spheres.
Okay, thanks, Henry. So this is joint work with Victor Magrand and Mathieu Scomra, who were here earlier this week. Okay, so let's dive into the problem that we want to talk about. So we're interested in a polynomial optimization problem, which is over the product of spheres, as the title was talking about. Okay, so first, let's clarify things a little bit. What is a sphere? We're talking about like a norm one vector in each one of these registers. So we have like m spheres, m registers, and in each register, we look at the norm one vector there. And I would like that the sphere is not just 2 points. So we say that the dimension is at least 2. So we have at least a circle or whatever you would like, but just not 2 points. And then we would like to look at some kind of subset of special polynomials. And for this, we say a small technical definition of a multi-homogeneous polynomial. Okay, so we have a tensor workshop, so we shouldn't be scared of indices. We have a vector of n vectors, or maybe this should say m. Okay, this should be an m. And each one of these vectors has dimension ni. Okay, so each one of these vectors lives in a register and on a sphere in that register. Okay, and we say f is multi-homogeneous if basically in each register we have a fixed degree. So then there's a di for every xi. So what does this look like? So in 2 registers, we have 2 dimensions and then 3 dimensions as an example. In the first polynomial, you have that the first register has degree 2. So x1 and then whatever precedes it, this always can have degree 2, while the second one has, second register has degree 1. Now, the second polynomial is homogeneous, but it doesn't have this nice structure where you have 1 degree in 1 register for every monomial. So here you see the first register has degree 3 and then degree 1. Okay, so it's homogeneous, not multi-homogeneous. And if you'd like, you can maybe just think multilinear. There we have degree 1 in every register. So that's hopefully a familiar and easy example. Okay, but these polynomials are nice, so we want to sort of restrict ourselves to them and prove like more specific results that can still apply to also homogeneous polynomials. Okay, so this is our problem. And since a lot of people are interested probably about complex variables, we can replace this with complex variables. So you just have the norm 1 subset in the complex plane or in the complex. And this is just the same thing as the real sphere with a double dimension. I mean, at least this is how we will look at it when we want to use our tools. We will just convert it to real variables.
So essentially the Hermitian form.
Yes, so like z. No, it's like z bar is z bar is equal to 1. Yeah. And for f, I mean, if we want to talk about a minimum, then we want to say that f is real valued. And again, we still say it's multi-homogeneous. Okay, so this is kind of this problem that we're interested in. And we'll use this symbol, so you can quickly recall it. So we would also maybe have some more flexibility. So we can introduce a more general form of this problem. So here you have the one we just saw, and you can see that it's equivalent to this problem. So that arrow points in both directions. So here we're taking the infimum over measures. So this set is the non-negative Borel measures on the product of spheres. And this is actually a probability measure. So you can think of mu being like a Dirac measure, and then this will pick out the point where f has the minimal value. This is how you can try to see that these are the same problem. Okay, but this probability measure constraint can be generalized, and we can write that the integral of hi, where hi is a polynomial, is equal to bi, a real number. Okay, so this just makes it a little bit more general in that we can have constraints on the measure, more than just that it's a probability measure. So here we have some primal dual interplay, and I'll talk about that a little bit later. But just to have this, there's a connection between these two problems. And we also give it this symbol so we can look it up quickly in our memory. Okay. So why use these two problems, or why study them, or why do you maybe care about them? So I'll try to convince you that they have good modeling power, that there's a lot of problems that can be cast in this form. So in just the polynomial setting, so I've talked before about this. So the best rank one approximating tensor. So this is a problem where you're given a tensor of any size, and you want to find a rank one tensor that best approximates it. And here you are optimizing a multilinear or a multi-quadratic polynomial on the product of spheres. So there's a SOS convexity. This is to test convexity of a polynomial. This is on two spheres. The clique problem from graph theory is also cast this way on two spheres. Okay, but then more relevant maybe is this problem from quantum information theory about finding the best separable state. So if you're given a state which is potentially entangled, you want to find the best separable state that approximates it. And then for this GMP problem, we saw in Monique's talk on Monday, the DPS hierarchy, which detects entanglement. So there you can cast it as a generalized moment problem. And also there's some problem from quantum optimal transport, and this can be cast on two spheres as well. Okay, so here's the word tensor and some quantum words. So hopefully this is relevant and now piqued your interest. So let's talk about how we solve these problems, because that's what will make them hopefully useful. So let's go a little bit more general. We have a polynomial optimization problem. We have a polynomial P, and we're trying to find the infimum on some semi-algebraic set K. So you're given equality and inequality constraints where S and J, or sorry, Si and Gj are polynomials. So now this can be also rewritten in a different way. So we did this measure kind of rewriting, but here now we rewrite it in like a question of positivity. So we look for the biggest number that you can take away from the polynomial such that it's still non-negative. You can think of this as taking away this kind of height and bringing it down to the 0 axis in one dimension. And now for this semi-algebraic set, we can, okay, sometimes it's called a relaxation. This is kind of like a strengthening. We look for polynomials which are very obviously non-negative. So here you have sums of squares, sigmas. So these are always non-negative. And the SIs are 0. So you can put a arbitrary multiplier there of a polynomial. And this would be by definition non-negative on the feasible set K. Okay, maybe now it's easier to find polynomials that give you this sort of positivity certificate, but it's still, the degree of these polynomials can be arbitrarily high, so it's still infinite dimensional of a problem. So then we just do a sort of the obvious thing of looking at a cap on the degree of the polynomials, and we have a finite dimensional problem, and this is a can be solved with a semi-definite program. Okay. This gives you what we call a hierarchy that will approach the minimum. And under an assumption called Archimedean assumption, where our semi-algebraic set has a ball constraint, which is usually okay for us to make and practice, then this asymptotically goes to the minimum. So this is kind of like the staircase from this cover slide where we climb up to the minimum. So it's a bit different from like a local solver where you have upper bounds on minima. Here we have lower bounds on minima. And also would like to say that there's also relaxation on the moment side. So maybe without getting technical, I just give sort of like a heuristic idea of this. It's like you look at the enthemum on one side, and this is kind of like the moment side. So you're driving down, and on the other side, you're driving up, you're looking for the supremum. And this is sort of what we call the SOS side. And we'll talk about what's going on here. But this can be called, like we do this at every level of the hierarchy. So P, T, SOS is here, and P, T, M, O, M is here. And this gives, this has this duality, primal dual relationship that we have in optimization. Okay. They are both growing, yes. They're both growing to the minimum asymptotically. Okay, so then is this staircase useful? Can we really climb it, and can we reach our goal? So I argue that there are some nice properties to be had when you apply them to the problems that we looked at before. So for the polynomial side, we have generically finite convergence. So this means that on the spheres, if you have this multi-homogeneous polynomial, for a generic multi-homogeneous polynomial, this will not just be asymptotic, but it will converge finitely. There's a strong convergence rate where this T is this index of the hierarchy. And then, was it yesterday, we heard from Jonas about, no, earlier than yesterday. I'm sorry, the week is blending together. So we saw about using symmetries and how that can make solving this problem more efficient. And when you have your problem in different registers on the sphere, symmetries, I think, can be easily found. There's also algebraic properties which are nice. So this is kind of some ongoing work where you can make these stairs sort of faster to climb, let's say. There's also nice solvers that can be used. And in general, actually, we only have to climb maybe 2 steps of the staircase to reach the minimum. And for the generalized moment problem, we have a recent work about duality attainment and strict feasibility. This is sort of talking about this sort of interplay, which I'll get into a little bit more. So since there's not so much time, I'll just talk about this kind of new contribution that we made. Any questions about this would be okay. Okay, so now It gets a little bit technical. So what is duality attainment? So if you recall, we have this SOS problem, and we relax it to have like a finite degree. So we have infinite dimensional problem and a finite dimensional problem. And actually in both, we can turn this soup into a max. So here I'm talking about the SOS thing, which is the dual of the moment. So for the dual of the GMP, which is also very similar to this, but there's a small technical difference. We need like an assumption. So you have this thing which I think maybe is looks technical, but it's basically the moment cone, if you are okay with that terminology. So we need that the right-hand side, which were these real numbers that we applied as constraints on the moments, that it's inside of the relative interior of this cone. So you can try to make it so that your problem fulfills this assumption, and then this will guarantee attainment. Okay, so what does this duality attainment mean? Maybe I can sort of wave my hands a bit. So imagine we have a gap here between these two. This would be called a duality gap. So we have two things. First, there may be a gap between these two things. But also, since this is a soup and this is an infimum, we may have it be the case that the soup will not actually be attained by the problem. So that means we have a sequence which reaches the supremum, but we don't actually, the final point is not feasible. So there's already examples in one dimension where this happens. And this makes it so that we can't get like an actual algebraic certificate potentially of like positivity or something that we want from our problem, especially when we're applying it to things, where we want to find the best state which is approximating something. And so there's also some numerical problems when this does not happen, because as I said, these are semi-definite programs, and they're solved by primal dual interior point methods. And there you have some problems if there's a gap here, first of all, but also further if this is really a sequence rather than you can actually have a feasible point which turns it into a maximum. And just an idea of what this was about. So we really just built on a lot of existing work and gave two proofs to this earlier theorem. So first, you look on the actual SOS side, and there you have the quadratic module is the feasible space. Okay, it doesn't matter what a quadratic module is, just the feasible space you look over. And we show if you show it's closed under this relative interior cone, like assumption, then you can show that the SOS side will be attained. And this builds on a lot of work already by Powers and Schreider and Murray Marshall and Marcus Weighofer and others also. So then there's also another way of giving the fact that both sides will be attained. And this is using more, let's say, classical optimization techniques of like strong duality. So showing that it's strictly feasible amounts to finding a Slater point, or maybe people call it some other things in different fields, but this is something that's like a strictly positive measure for the moment problem. And this, we used some results. I always mispronounce this person's name. Okay, maybe I'll just not do that. So the strict feasibility point also is somehow makes solvers happy, and this can give good implications to numerical computations. So the implications of this theorem I already kind of talked about a bit. So you have existence of optimality certificates. This is when you have the infinite dimensional problem. So this means that you really can, maybe if you have a theorem where you need an algebraic certificate of a certain bound, you have this. You don't just have a sequence that approaches it. And we talked about the stability that this offers to solvers. Okay, so this was hopefully the only technical part. Any questions? Yeah? It's okay. Just can you repeat it? So if you think of the optimization problem, this is a chart. So for a general semi-definite program, you're looking for the minimum, let's say, or the infimum of some matrix, and you take the trace inner product with a cost matrix, and now you want that this matrix is positive semi-definite. And another way to say this is that this X is inside the cone of positive semi-definite matrices. And then the dual comes from taking the dual cone here, which in this case is the same cone. But so in conic programming, sometimes the dual cone is different. So when you have a more general problem where it's any kind of cone, the problem will, where you take the soup, will be over the dual cone here. Yes, so here, I mean, this is just in PSD space without any restrictions. I mean, you usually have something like XAI is equal to BI. So this is like some kind of slice of the PSD cone. And then when you dualize this problem, you dualize the cone, it stays the same, but then these sort of A, B, and C move around in some way that I will not attempt. Okay, so then to summarize, we look at these two problems where the polynomial optimization problem is a more specific version of this generalized moment problem. And we talked about how they model many problems and how, I can't, okay, there's one more bullet, but I think it's, okay, this is gone, so it's okay. But so hopefully this would be, if you have some problems from tensor optimization, it may be possible to cast your problem in this form, and hopefully that would be useful for you. That's all. Yeah. So, okay, if I understand the question, why do I ask that it's homogeneous or multi-homogeneous? So, I mean, to prove these results, it's harder to make this restriction. So, if we don't have this multi-homogeneous structure, which is much more rigid than, for example, homogeneous structure, the results still pass through. But it's much harder to prove them when you have this extra condition, especially when you do something generically, because if you have something So when we apply this problem to like tensor optimization, the polynomial will come straight from the tensor coefficients, and then it will really be, this is the form of it, and you can't add like a homogeneous monomial because this is not in the tensor. Yeah. Yes. So we wanted to. Yes, yes, they do. Yeah, but I guess so. I say it's a multi-homogeneous because it's harder to show it for the multi-homogeneous one, but it applies to not restricting to this structure. Yeah.
Are there any other questions?
Yeah. Yes, you're looking that to check your pseudo moment matrix, pseudo moment sequence is coming from a measure. So you mean this is like when you have a finite convergence result? So, but what was the question? Sorry. No, you don't have a guarantee on that unless you have shown that this is, there's some kind of flat extension kind of condition that holds. Yeah, so in this case, when we have finite convergence, this flat extension result also comes. So you have that at a finite order, generically, you will have this flat extension condition satisfied, which means it will come from a measure. But not always, yeah. Did that answer the question? Okay.
Wonderful. Then any other questions? You can ask me. Right, and let's thank the speaker again.